Well, welcome everybody to Arxiv Dives with Oxen.ai. Each week, we deep dive into an archive paper and try to make ourselves a little smarter. So thanks for taking some time out of your day on Friday. Means a lot. Today, we're going over the CLIP paper from the team at OpenAI. CLIP stands for Contrastive Language Image Retraining. So this paper in general is pretty interesting. It mainly talks about what's called zero-shot image classification, but it is actually also the backbone for a lot of these generative image and video systems that we see out there today, like DALL-E or Stable Diffusion. So I would just keep that in mind as we're going through the paper. We're going to be talking a lot about image classification, but this is a building block for a lot of the generative AI techniques as well, because it does a great job of mapping text, phrases, and sentences into the same dimensional space as images, which is pretty cool. So last week, we went over the vision transformers. VIT, if you missed it, we have a whole blog here. This work builds on top of that work because they use a vision transformer internally. So we won't be like diving too deep into the details of that, but just as a reference point, when we talk about VIT, we have that example from last week. And this paper is all about image classification, which can be used for many different tasks, like automatically tagging or sorting through large sets of images, filtering out content based off of a class, recommending ads on user-generated data, analyzing a video frame by frame. Lots of different use cases for image classification. But the problem with a lot of image classification models is they're limited to a fixed set of categories. So if you want to detect an object that's not in the original training data, you have to retrain the model and teach it about that new category. So the main takeaway from this paper is that CLIP allows you to predict without a fixed set of categories, and you're only limited by what a language model knows about the world and what it's learned during its pre-training step, which is really cool. So to make this concrete, I have some data here. It's this Oxford Pets data set. And I took the vision transformer that we talked about last week, and I ran it on a bunch of images from this pet data set that has like 37 different classifications of pets. And I have the label name right here, and then I have the prediction that came out of the model here. And you can see that this model was trained on ImageNet, which ImageNet has 21,000 categories of things that it can classify. And a lot of those are pets. But if you notice, like this one is a cat that was labeled Berman, and the model predicted Persian cat. So we actually said that this was an incorrect classification. Or this one is Leon Burger, and we said Leon Berg. So it also counted that as incorrect. Now, obviously, there's some mapping you could do between these terms if you wanted to do kind of just like a code layer on top that fixes some of these problems. But I went through and I computed the just raw accuracy of the vision transformer on this pet data set. And if you like downcase and do a string match on any of these categories out here, it actually only got 43% accuracy on this data set. So that's like the vision transformer that was trained on ImageNet. Now you could fine tune this model and you could teach it these categories. But what is crazy is I ran the same thing on CLIP, and I just told it, okay, I want you to use these categories, which will show how you like practically do that a little later. But Clip got 91% out of the gate without any training, without any mapping. And you can see it got the labels exactly correct in all of these, except for the Berman one, again, which I don't even know what a Berman is. Maybe somebody can tell me, but it classified it as a ragdoll in this scenario. But pretty cool that you can do that without actually training. Next week, we're going to be extending the Arxiv Dive series into what we call practical Arxiv Dives, and I'll show you how to write the code to actually run something like this, so we can play around with the data live and play around with the code live. So I think that'll be fun. But back to how they do this. So again, this is the OpenAI team. So they love to do these large pre-training steps inspired by GPT-3, where if you train on a large set of data, they found that now you can use end-shot learning off of that data and predict a lot of things just based off of this large pre-training data set. And in this case, they do what's called zero-shot learning. So they don't even give it any examples. They just give it the names, the possible names of the classes that you want to go into, and it can automatically figure out how to classify into those. So what they did is they created a data set of 400 million image to text pairs that was crawled from the internet. They didn't go too deeply into exactly how they got this data set, and they actually didn't release the data set either. But you can think of it as they crawled and found the alt text on HTML images and just collected that as the pairs of descriptions and images. So what that looks like is something like this. This picture is from this generative AI book that I would also recommend, that we kind of went over as a internal Oxen team a while back. But you have like a cute banana made from modeling clay, and it looks like this, or a television studio about to broadcast, and it looks like this. And a lot of people already put this alt description for their images within their web pages for like people that have disabilities or for web crawlers to read what the image is about and index them better. So it's actually a great place to just like collect a really large data set. So after they collected the 400 million image to text pairs, they evaluated it on 30 different computer vision tasks. So those range from the pet example that I had above, which is called Oxford 3 Pets dataset with 37 different classes, to classifying cars or aircrafts or birds or satellite imagery or emotional detection, etc. So a bunch of different interesting data sets that they evaluated on. And what is crazy is they match the accuracy of a ResNet trained on ImageNet with zero shot. And this ResNet was trained on like 1.2 million images. And with Clip, you can just do this with zero shot given the pre-training. So how does this work under the hood? They call it Clip because the name again stands for, which I didn't put in here. The name stands for Contrastive Language Image Pre-Training, which I'll put right here just so we have the name in our brains. And what they do is they jointly train two models. So they have a text encoder and they have an image encoder. And we've gone over some of these models in the past. The text encoder is a transformer. The image encoder is also a transformer. And the key insight is they gather a matrix of n by n text and image pairs, and they jointly train the two models to maximize the cosine similarity of pairs that match, and then minimize the cosine similarity of pairs that don't match. So you could imagine they have 4 different sentences up here, and then they have 4 different images right here, or, n. They encode each one of them into an embedding, each piece of text into embedding, and then they encode each image into an embedding. Each one of these are just like a vector representation of it. And then what they want to do is for each matching image text pair, they want the cosine similarity to be 1. And then they just kind of assume from the nature of this large data set that any of the other pairs are going to be incorrect descriptions for the image. So this one might say Pepper the Aussie dog, and this one might say a red Corvette or something. And so they're trying to get this value to be 1, and they're trying to get this value to be 0. And if you do this over and over again, eventually the image encoder generates embeddings that look a lot like the embeddings that come out of the text encoder, which is a really nice property to have. So when it comes to inference time, that's kind of like training, just setting up this infrastructure so that you can maximize the ones that are the same and minimize the ones that are different. At inference time or at test time, what you do is you take both of those models that you trained, and you take a list of classes. So in this case, maybe we're trying to classify between planes, cars, dogs, and birds. They generate a short snippet of text, and in this case, they use a photo of a blank. And so they have 4 different sentences that they encode: a photo of a plane, a photo of a car, a photo of a dog, and a photo of a bird. They encode all of those with the text encoder, and then they have the image that you want to know the new class of. They feed that through the image encoder. They compute the scores for each one of these, and then they say, or take the cosine similarity between each piece of text and that image, and then they just take the one with the highest score, and that's your classification. So, you'll get 1 score out for a photo of a plane that might be like 0.01, a score out for a photo of a car that might be 0.05, and then a photo of a dog might have like 0.09, and that's how they get the classification. And Ankar asked, what is the dimension of the embeddings? That is a good question. In this exact paper, they use a transformer with a 512 dimensional representation. So both of these embeddings are 1 by 512. Evan, yeah.
You might have already answered this. So is the ultimate prediction the class number, or is it the text?
It is which one of the texts has the highest cosine similarity to the image. So they actually score each piece of text, and they'll get a different score from each, and then they just take the max. And then
so it's discriminating between the predefined classes. So basically, if you showed it something it had never seen before, it wouldn't be able to describe it.
Well, that's the cool part, is you can change what these classes are on the fly.
Oh.
And so they happen to have these 4 classes, but you could have your dictionary of classes that you want to classify into.
Okay, I see what you mean. Because T1, T2, T3 are all based on the encoding.
Yep.
Okay, thanks.
Yep, totally. Daniel.
Thank you. I was just, I've heard of CLIP before, and I'm realizing after you said what you just mentioned, am I correct in understanding that then the whole purpose of CLIP was to develop this model with basically an understanding of concepts in like images and text rather than, because I always associate Clip with generating images, but I realize now that that might not be immediately the case.
Well, yeah, that's super interesting because I also associate it with generating images. And when I went back to go read the paper, the initial use case was actually image classification. And then I think that same team at OpenAI was like, wait, if we can embed the text and the image into the same space, there's no reason we couldn't go from that text embedding to generate an image. So they kind of go hand in hand together. But the initial use case was classification.
Okay, thank you.
Yeah. Cool. So they talk about creating a...
Sorry, Greg, looks like we had a couple more. I don't know if you wanted to keep moving, but there are a couple more hands.
Oh, yeah, for sure. Who's next? I can't even see the queue.
Rohan, you want to go?
Yeah, sure. So I just have a question about how you mentioned that some of the image embeddings have been set to 0, right? So I just wanted to know, could you explain brief yet again how you mentioned the clip team set the values of some of those image embeddings as 0 to match it with a specific text embedding so as to create those image text pairs?
Yeah, so they actually don't set the embedding to 0. They just set the score that they expect out of the image embedding text pair to have a cosine similarity of 0. So cosine similarity, you can take two vectors and compare kind of each element of them. And if they're really close in like directional values, so they have higher values over here and lower values over here, the cosine similarity is going to be 1. And then if they're very vectors that are going in different directions, they have a cosine similarity of 0. So the embeddings themselves aren't 0, but the comparison between them would give you a cosine similarity of 0 for the pairs that don't go together, and then a cosine similarity of 1 for the pairs that do go together.
Okay, got it. So they're not setting the embeddings as 0, but the expected output, right?
Yes.
Output class. Okay.
Yep. Totally. Is there another one? Ken?
Yes,
Yeah.
one left.
Hi, how's it going? This is the first time I'm joining this. I just saw it on Reddit when I asked someone if there are any discussion groups around this. So thank you for having these events. Looks really interesting. I was just wondering if you could talk about how they are able to get the I values over there, the I embeddings, and how that works. If that's okay. Like I'm a little more familiar with the T part, but I just did not understand. I understand how they interact with each other, like I and T, but I just don't have much background information on how I is achieved in there. And I
Yeah.
was wondering, like, if you could just give a brief summary on that, if possible.
Yeah, so it's actually very similar to the T. So the T is like a large language model text encoder, and then the I is like a vision transformer image encoder. And you could actually swap out a lot of different image models here, and they do it in the paper. So they compare, what if you had a ResNet as the image encoder? What if you had a vision transformer as the image encoder? And then they do that same kind of step where they look at an embedding layer deep within the network, and then that's what they're taking for I, if that makes sense.
I see. Thank you so much. Yeah. Makes sense.
Sorry, to summarize what you just said, are you saying that essentially they trained ResNet and then they just grabbed one of the intermediate layer representations for the encoder?
Yep, and they do it all from scratch in here, so it's not like a pre-trained ResNet. They're training the image encoder as they're going through these image text pairs.
Yeah.
And it back propagates like all the way from, did you get a cosine similarity of 1 or 0 through the image encoder and through the text encoder. Gotcha.
Yeah, so that they didn't pre-train the image encoder. It's all from 0.
Yep. Yeah, but they have like a data set of 400 million images, so it is a pretty big training instance. Cool. So back to like that training data set itself, they actually went through and generated 500,000 queries of like words or phrases from the English version of Wikipedia, and they required that that word or phrase appeared at least 100 times. So that's kind of how they generated their first set of web queries. And then they went and found images of all of those things, and they tried to balance out the data set to make sure there was at least 20,000 image text pairs per image or per query. And then they must have done some filtering beyond that. But that's kind of the process that they did. They call this data set WIT for web image text, but it's another example of a paper that's open and like an implementation that's open and a model that's open, but the data set itself is kind of like the proprietary stuff that OpenAI kept close to their chest. Obviously, they went and made Dolly and stuff like that afterwards. That's just a sense of the data set. To your questions before, for the image encoders, they try 2 different image encoders, a ResNet 50 and a VIT, Vision Transformer. And within even both of those, they try 5 different ResNets and 3 different Vision Transformers. So you can read the paper for details on all of those. The text encoder itself, so the large language model, half of it, they use a 63 million parameter 12-layer transformer with 8 attention heads and this 512 dimensional representation. To answer that question before, they use a vocabulary size of almost 50,000 byte pair encoding. So these are like sub words. And so this is one of the benefits of using an LLM and like a byte pair encoding is now you can have any class of output that you want there rather than the fixed set of classes that you have with a traditional image classification. And they state that the ResNet model took 18 days to train on a bunch of V100s, and the Vision Transformer took 12 days to train on a smaller set of GPUs, but all in all, a pretty computationally expensive process to train any of these. And they say that the best clip model they found was a Vision Transformer. If you look at the Vision Transformer paper, there's like different sizes of it. So the Vision Transformer large with a patch size of 14 and a resolution of 336. Good question. The way they created the data set, it seems like there could be some overlap with ImageNet, because could this potentially be the reason why they get such high accuracy on ImageNet out of the box? They do some studies on that below, but yeah, there is a lot of potential for overlap in the data sets. So some of the experiments that they do, when they say 0-shot, they mean having the model generalized to unseen object categories. And where this is pretty evident is you can look at like the task of classifying a banana from all of these different data sets. If you look at a ResNet 101 that was just trained on ImageNet, if you show it something like a sketch of a banana or a noisier image of a rotten banana, ResNet actually performs much worse. But since the clip model has seen a wider variety of images from all of the internet, it's actually much easier able to generalize to things like a sketch of a banana or a very noisy image here. You can see that these numbers kind of like blow the ResNet out of the water when you do data distribution shift outside of the regular ImageNet distribution. And they looked at some previous work of trying to do 0-shot image classification transfer, and it just blows these previous methods out of the water, like going from 11% accuracy to 76 or 72 to 98. Pretty wild. Ben.
There was a really good point in the chat that was talking about some of the ways through which they obtained their data set sounded similar to the way the ImageNet was originally curated. Do you know, did they mention doing any checks against ImageNet just to make sure there was no overlap?
Yeah, I believe they did. I'm just going to pull up. Yeah, here we go. I just searched for overlap in the paper, and it's on page 11. So they say this could be, so let's see. Qualitatively, CLIP model learns a wider variety of tasks than has previously been demonstrated in a single computer vision model. This could be argued as a form of selection bias of the study towards tasks with overlap of ImageNet. To address this, we measure performance on a broader set of 27 data sets that aren't in ImageNet, from like German traffic signs to satellite imagery, and they show that the model still generalizes to these things. So that's what they said about that.
Doesn't seem like they did any, they were aware of it and didn't do any direct checking on it.
Yeah, I believe that is correct. That'd be very interesting to try to like verify how much overlap there was there.
If only they released the data.
Yeah, that would help. It is funny though, because in practical use cases is like, how much do you really care about that if you're just generating images? So they say, you know, part of the reason in this giant leap of performance that's not controlled for, if you're comparing against prior art, is they use a way bigger data set, they use way more compute than this model did, and they use larger models in general. So although they say they blow these out of the water, it's not really apples to apples. And I posted this in our Discord, but I thought this was one of the most entertaining quotes from the paper. Is they were talking about going through the data sets and looking at how well it performs on like flowers or on German traffic signs. And they have a footnote that says, Alex learned more about flower species and German traffic signs over the course of this project than he originally anticipated, which I can totally relate to as somebody training these models. I feel like you just learn all the nuances. An interesting point of these zero-shot transfers is what they call polysemy, and you might recognize some of this from our NLP work. But for example, in ImageNet, there are multiple meanings of the same word might be included in different classes of the same data set. So like, for example, you might have construction cranes that build things and cranes that fly. Or in the Oxford PET3 data set, there's a class called Boxer, which is clearly a dog in this context. But there's also Boxer, the athlete. So if you just do the technique that they were talking about before of embedding a phrase that is like a photo of a X, the text encoder has a difficult job disambiguating between Boxer, the athlete, or Boxer, the dog. So if you know the type of data set that you're evaluating on downstream, they actually did a little hack here and said a photo of a label and then a type of pet to narrow down the types of things you were looking at. And that's kind of like a cool little hack on prompt engineering the label is what they call it. And something that you can do with a CLIP type model that you couldn't necessarily do with a standard image classification model. Because with a CLIP model, you can add little clues into the prompt. And if you add that little clue for every single possible label that you're going to run through it, then you get a higher accuracy classification out. They said that adding a photo of A to the prompt increased the accuracy by 1.3%. And then adding something like a photo of a and then type of pet increased the accuracy an additional like 3.5% on data sets like the pet one. They even go as far as ensembling 80 different context prompts for some of them. So you could have like a bunch of different ways of giving the model a clue about the distribution of data that you're classifying, and then average all of those things, which is pretty cool. And then finally, how they compare. I think the most interesting part about how they compare a lot of these models is they take the CLIP model and they compare it to a logistic regression on the features of a ResNet that was just trained on, ImageNet or something like that. And they show for a lot of data sets, zero-shot CLIP just outperforms out of the box. And for a lot of data sets, it doesn't. And if you look at the types of data sets here, it is the types of data sets that have more common things that would be on the internet that people like to put descriptions of, like cars, my cool new red Mustang, or countries that they visited, or food that they've taken images of, or kinetics is like a action classification data set. And then for things like satellite imagery or more medical data sets, training on that actual distribution does way better than the zero-shot classification. So just another proof point that, just because zero-shot does better in general doesn't mean it's going to do better on your data set. And so that's interesting. They also decide to try to say, okay, we looked at zero-shot performance. What if we show you one image? What if we show the CLIP model one image from that category, 2 images from that category, 4 images, and train that last layer, a logistic regression model on top of it? And what's kind of shocking is that the zero-shot actually does better than the 1-shot, the 2-shot, or the 4-shot. And they argue that one, you can add additional context to the prompt to disambiguate in a zero-shot context. And if you think of it like, if you're trying to pick one canonical image that really represents this class, it might actually bias the model more towards making an incorrect prediction than just using the language model itself. But as you add more and more examples, eventually CLIP outperforms all of these ones. So thought that was super interesting. And then they also did a comparison against human performance, which I thought was interesting to think about. And like, if you just think of the Oxford pet data set again, I mean, I didn't know the names of half of those cat breeds in there. Like, I pretty much just know cat or dog and maybe some dogs. So they showed a bunch of humans, like all of those pet breeds, and maybe one example image from each pet breed, and then asked humans to classify the images if they've only seen one. And we do pretty terrible at that compared to CLIP, which totally makes sense to me, especially if you don't have background knowledge about that domain. It is a pretty hard task just to see one image and try to generalize that. Is that a Siamese cat, or is that I don't even remember the names of the other ones. But that was cool. I think broader impacts of these things are obviously that now, this is an open source model, and this allows anybody to roll your own classifier without much training. And so this is great for all of those use cases I talked about before of like action recognition, object classification, facial, emotional facial emotion recognition, but obviously has some implications for privacy, surveillance, all that kind of stuff. If you're interested in diving more into that, they have full studies at the end of the paper on race and gender and other like socially harmful labels that might be in the data set. Like, for example, what demographics are more associated with crimes, just given the text and image pairs that they crawled from the internet. So at the end of the paper, they dive kind of into those if you're interested in that. And I'd say, in conclusion, this paper talks a lot about image classification, but I do think it's important to recognize that they also use this for a lot of the generative image stuff. That's kind of what I want to get into next is, okay, they learned that you can map images and text into the same space. Now, how do they take a pre-trained clip model and turn that into DALL-E, for example? So we'll be going over that in the next couple weeks. And yeah, curious to hear your guys' takes. I would, like I said, next Wednesday, we're going to be showing you the code to actually run a clip model and run a vision transformer, and we're going to run it on some actual data sets. So I'd love for you to join for that. But other than that, I hope this was helpful. And does anybody have any other higher level questions of places they're confused or stuff they don't want to talk about?
And I just put into the chat the link for Wednesday sessions, which we're calling Practical ML Dives. If you want to get more hands-on, you can click there and see ideas to make it more real. And then right above that's the link to all the links. So there's a Notion doc that has everything: Discord, Practical ML, the blog, YouTube, everything consolidated for folks.
Yeah, and Nina, we're going to be posting the notebook or the code to a GitHub, so anybody can follow along later. And we also post all of these notes on the blog, so if you can't make
Awesome,
this
thank
session.
you.
Yeah. Cool. Well, I'm going to stop the recording because I know some people like to chime in without being recorded. So thanks for joining in, everyone, and we'll just have a free forum chat after this.